Welcome to Chapter 4 of the LLM Basics Series. Training an LLM is only half the battle. We also need to serve it efficiently. This chapter covers the techniques that make LLMs fast enough for real-world applications. You'll learn about quantization, caching, and specialized serving frameworks that enable millions of users to interact with LLMs every day. LLM inference has two distinct phases. The prefill phase processes the entire input prompt in parallel. This is compute-bound and determines time to first token. The decode phase generates output tokens one at a time, each depending on all previous tokens. This is memory-bound and determines generation speed. Understanding this distinction is crucial because different optimizations target different phases. The KV cache is a fundamental optimization for autoregressive generation. Without it, we'd recompute attention for all previous tokens at each step, incredibly wasteful. The KV cache stores the key and value projections from previous tokens, so we only compute attention for the new token. The trade-off is memory usage, which grows linearly with sequence length. Managing this cache efficiently is critical for long-context applications. Quantization reduces model size and increases speed by using lower precision numbers. Standard training uses 32-bit floats, but we can often use 16-bit, 8-bit, or even 4-bit representations with minimal quality loss. Going from 16-bit to 4-bit reduces model size by 4x and significantly speeds up inference. The key is quantizing carefully to preserve the most important weights. This makes it possible to run large models on consumer hardware. Several quantization methods have emerged. GPTQ uses calibration data to minimize quantization error layer by layer. It's popular for GPU deployment. AWQ, or activation-aware quantization, identifies and preserves the most important weights based on activation patterns. GGUF is designed for CPU inference and is widely used with Llama, CPP for local deployment. Each method has different trade-offs between quality, speed, and hardware compatibility. VLLM introduced page attention, a breakthrough in LLM serving efficiency. Traditional systems waste memory due to fragmentation. Each request reserves maximum possible memory, even if unused. Page detention manages KV cache like operating system virtual memory, allocating small pages as needed. Combined with continuous batching, VLLM achieves 2 to 4 times higher throughput than naive implementations. It's become the standard for production LLM serving. TensorRT, LLM is NVIDIA's optimized inference library that squeezes maximum performance from their GPUs. It uses kernel fusion to reduce memory transfers, FP8 precision on newer hardware, and sophisticated graph optimizations. On H100 GPUs, it can achieve significantly higher throughput than generic frameworks. For production deployments at scale, hardware-specific optimization like this is essential for cost efficiency. Speculative decoding is a clever technique to speed up autoregressive generation. A small, fast, draft model proposes multiple tokens ahead. Then the large model verifies all proposed tokens in a single parallel forward pass. Accepted tokens are kept. Rejected ones trigger fallback to standard decoding from that point. Since verification is parallel, this can achieve 1.5 to 2x speedup while producing identical outputs to standard decoding. Deploying LLMs in production requires careful attention to several best practices. Batch requests together to maximize GPU utilization. Use appropriate quantization for your latency and quality requirements. Enable KV caching and choose serving frameworks like VLLM that manage it efficiently. Select hardware based on your workload H100s for high throughput, consumer GPUs for cost-sensitive applications. Monitor latency percentiles and auto-scale based on demand. Excellent work! You now understand how to make LLM inference efficient. We covered the prefill and decode phases, KV caching for avoiding redundant computation, and quantization for reducing model size. We explored VLLM's page detention and TensorRT LLM's hardware optimizations, plus speculative decoding for faster generation. In our final chapter, we'll explore practical applications including RAG, agents, and production deployment patterns. See you there.